Alright folks, third and final video from section 5.1, working with radicals. In this video we are going to add subtract radicals, and the instructions are, I guess, part of the question here for the example. We're going to simplify and combine like terms. So remember, to simplify radicals, what we've got to do is pull anything out from under the radical sign that can come out. So in this case, 3 square root of 2, there is nothing I can do with that. 50, however, 50 we can work with. If you are, well, you might see the connection for 50 right away, or you might have to think about it a little bit. When I look at 50, I see 25 times 2. So I'm going to express 50 as the square root of 25 times 2. The plus 3 root 2 I am going to leave alone because it cannot be simplified. Square root of 25 is 5. So this can be separated. Square root of 25 times the square root of 2, and I'll do this over on the side. 25 times 2. I can write that as, I guess I'll go all the way back to the 50. So square root of 50 is the square root of 25 times 2 is the square root of 25 times the square root of 2. And the square root of 25, the positive root anyway, is 5. So 50 can be expressed as 5 times the square root of 2. And that's exactly what I'm going to do here. Square root of 25 root 2 is 5 times the square root of 2 plus 3 times the square root of 2. And now we have like radicals. This is just like 5x plus 3x, only instead of x, it's root 2. So we can write this as 8 times the square root of 2, or 8 root 2. If you got to 50 and you were struggling with pulling out the 25, start a factor tree, a prime factor tree for 50. So 50, you might have said, all right, well, that's 5 times 10. 5 times 10. 5 is a prime number, so 5 comes down. 10 is going to be 5 times 2. And then you're done, and there's your 5 times 5. So if you wanted to, you could think of this as the square root of 5 times 5 times 2. And then the square root of 5 times 5 is just going to be 5 root 2. Okay, so whether you see it from the prime factor tree or whether you grabbed the 25 right away, same result. Okay, another example, a little bit trickier. Okay, so now we've got multiple things going on here. We've got a negative radical, which is okay for the coefficient, not okay in this case because it's a square root. So the radicand couldn't be negative, but the coefficient could be negative 1. We have 3 root 5, we've got square root of 80, and we've got minus 2 times the square root of 12. Okay, so let's simplify these, and I think I'll do it over here on the side because that just makes more sense to me. Let's look at the square root of 27. And I'm going to leave the I'll bring the minus sign. Okay, so 27, if I start thinking about that in terms of factors, 27 is going to be 9 times 3. Okay, and 9 is a perfect square. So I would probably stop here. You could go that it's 3 times 3 times 3 if you wanted to. But I would likely seize onto that 9. So I'm going to write negative 27 as negative the square root of 9 times 3, which is negative the square root of 9 times the square root of 3. Square root of 9 I can write as 3, so this is negative 3 root 3. So on my second line, my negative 27 is going to be negative 3 root 3. Okay. 3 root 5 I can't do anything with, so I'm just going to write plus 3 root 5. That's as simple as it gets. Notice that these are not like radicals. Okay, square root of 3 is not like the square root of 5. We'd need the exact same index, which we have, but we'd also need the same radicand. So those can't go together. So now let's take a look at that 180. Or sorry, not 180, about the 80. So square root of 80. Square root of 80. So again, factor tree 80 is a couple of ways to go about it. So I'm going to go 8 times 10. 8 is 2 times 4. And 10 is 2 times 5. So, and now the 2 comes down. 4 is 2 times 2. Times 2 times 5. All right. So 2 times 2 times 2 times 2. Well, that's 4 times 4. Times 5. Or I prefer to think of it as 16 times 5. Okay, so square root of 80 is going to be the square root of 16 times 5, which is the square root of 16 times the square root of 5, which is 4 root 5. Okay, so back up here, my minus 80, so don't forget the minus sign, is minus 4 root 5. Okay, so there is that one. And last but not least, that leaves me with 2 root 12. 2 root 12, and it also leaves me with not a lot of space, but I think I can make this work. So I'll go over here. 2 root 12, and again, I'm just going to leave the minus sign up here. It's not going anywhere. So 2 root 12. 12 is 4 times 3. And 4 is a perfect square. Again, if you wanted to complete this, it's not 3, sorry. If you wanted to complete this, it would be 2 times 2 times 3. But I'd probably stop at 4. So that means 2 root 12 equals 2 times the square root of 4 times 3 equals 2 times the square root of 4 times the square root of 3. Square root of 4 is 2, so that's 2 times the square root of 3, also known as 4 root 3. All right, so minus 2 root 12 comes down as minus 4 root 3. Okay, so now we can start combining our like terms. And in terms of like terms, I've got 2 root 3's, so I have minus 3 root 3, and I have minus 4 root 3. So this is, again, you want to think of this like negative 3x and negative 4x. If I have 3 negative x's and 4 negative x's, then my relationship history is really my own fault. No. If I have 3 negative x's and 4 negative x's, then I'd have 7 negative x's. So negative 3 root 3 and negative 4 root 3 will simplify as negative 7 root 3. And now I've got 3 root 5 and negative 4 root 5. So those are my like radicals because they're both square root of 5. So positive 3 and negative 4 is going to be negative 1. So I would write that as minus root 5. So that is as simple as this one gets. 7 root 3 minus root 5. Or if negative 7 root 3, sorry, minus root 5. Or if you had preferred, you could write it as minus root 5 minus 7 root 3. That would be equivalent. Okay. So that is that. And one more, because why not? Okay, so we've got the square root of 4c minus 4 the square root of 9c. C is greater than or equal to 0. So we've just got our restriction on here to remind us that in both of these cases, we can't have a negative value for c, because then we'd be trying to square root a negative number. All right, but for the most part, we can largely ignore this as we solve the question. So we're going to simplify each part of this. And I think I've got room. I'm just going to do this one as I go. So first term, square root of 4c, I'm going to split it apart immediately. It's the square root of 4 times the square root of c. Second term, I've got minus 4. 9 is a perfect square, so I'm going to go the square root of 9 times the square root of c. Square root of 4 is 2, so root 4 root c is 2 root c, and square root of 9 is 3, so this becomes minus 4 times 3 times root c, not root 3. C. There we go. Okay, so I can simplify that just a tiny bit more. And I end up with 2 root c minus 12 root c, because 4 3s are 12, and 2 root c minus 12 root c is minus 10 root c. And that is it. That one is done. See if I can get 2 videos in a row. Nope, I'm over 10 minutes. I was going to say under 10 minutes. Yeah. So that is that. That's basically adding and subtracting. You're combining like terms. This should remind you very much of previous work you've done with polynomials. Okay, last one, and I've saved the best for last. It says, consider the design shown for a skateboard ramp. What is the exact distance across the base? So across the base, as indicated here. Now, we've got an angle, and we've got an opposite side. And to do this, it might not be immediately obvious, but we're going to need to do a little bit of trigonometry. And in this case, since this is my angle, and this is my opposite side, the value that I'm interested in is going to be my adjacent side, in both triangles actually. So opposite and adjacent hopefully will remind you of the tangent function. So tan theta opposite over adjacent, or OPP ADJ. All right, so I am going to break this apart. I'm going to call this L1. So that's from there to there. And I'm going to do that in blue. And I'm going to call this L2. And that's from there to there. And I will do that in red for no particular reason, except so that they're easy to keep track of. All right. So tangent is opposite over adjacent. Oh, the other thing that I forgot to mention that you might be wondering, why are you getting so excited with tangent? 30 degrees is a special angle. Hopefully you will recall. And the tangent of 30 degrees is 1 over root 3. So recall tan 30, 1 over the square root of 3. Yeah, so that's going to be useful here in a second. Now also recall that this wouldn't be a proper way, this wouldn't be a simplified radical, 1 over root 3, but it's a convenient radical when you're dealing with tangents sometimes, so we're going to leave it there. Right, so L1, let's take a look at that triangle for L1. So we're going to go tangent of 30 degrees in triangle 1 is opposite over adjacent is 40 centimeters divided by L1. Okay, and I'm going to drop the units here. Our numbers will come out in centimeters. It pains me a little bit, but they will get, it just gets cumbersome. So tan 30 is going to come down as 1 over root 3. And this is going to come down as 40 over L1. Right, so I don't like having the variable on the bottom, so I'm going to multiply both sides by L1, and I'm going to multiply both sides by root 3. Okay, so to straighten this out, I'm going to take this side and multiply it by L. Hold on there. Pen tool is not my friend at the moment. Okay, so I'm going to multiply this side by L1 times the square root of 3. I'm going to multiply this side by L1 times the square root of 3. When I do that, root 3 and root 3 will cancel on the left. Or by cancel, I mean root 3 divided by itself would be 1. And on the right-hand side, L1 divided by L1 would be 1. So those go away. And I am left with L1 times 1 is L1. And that is going to be 40 root 3. Okay, so there's L1 expressed exactly. So now let's do the exact, well not the exact, but we'll do a very similar idea over for triangle 2. So once again, tan 30 is opposite over adjacent. And this was awkward, so I'm not going to do that again. So tan 30 is 1 over root 3. And opposite over adjacent, in this case, is 30 over L2. So 1 over root 3, I don't know why I was getting ready to multiply, equals 30 centimeters over L2. And we do the exact same trick that we did over here. We're going to multiply this side by L2 root 3. We're going to multiply this side by L2 root 3. Root 3 divided by root 3 is 1. L2 divided by L2 is 1. And now L2 is equal to 30 root 3. Okay. Okay, so but we're not quite done because we want the exact distance across the base. So my exact distance, the answer that I'm looking for, is L1 plus L2. Okay, so L1 we said was 40 root 3 plus L2 was 30 root 3. So if I have 40 root 3's and you give me 30 more root 3's, I will have 70 root 3's, and my total units, the answer is going to wind up being 70 root 3 centimeters. So 70 root 3, and my units will be centimeters. That is the exact distance across the base. There's nothing else we can do to simplify this further. Root 3 is as simple as root 3 gets. And yeah, that is it. All right. We didn't talk much about restrictions in this section other than to mention them at the beginning and occasionally when we had square roots, just saying, oh, by the way, a can't be negative. The next section we're going to be multiplying and dividing. So restrictions will get mentioned passingly there. And then by the time we get to section 5.3, we'll actually be solving radical equations. And that is where restrictions are really going to start to become a bit more prominent. So thank you for watching this far, and take care.